Hello, everyone, and thank you for joining the course of Fundamental of Robot Control, Week 1, Introduction and Mechanical Modeling by me, your lecturer for today, Sinan Ibrahim. And the course overview, we will see an introduction of robot control, mechanical modeling, linear control, PD, PID, as we see here in the picture, and Lyapunov functions, of course, and stability, feedback linearization, inverse dynamics, robust and adaptive control. For this lab, we will talk about motivations for robot control, discussing what makes up a control system, control design, and what's the objective of it, understanding the mechanical model and how to make a mechanical model using state space equations. Of course, we will solve a few exercises. For the motivation, we will start by demonstrating a swing up of a triple pendulum. This process is highly nonlinear and it's very hard to design the control for it. And here we have the famous Atlas robot doing a backflip back in 2017. And we see how this field is very interesting and important to control the robot. So what does a typical control system consist of? First, we have the process of control, which is the object that we're controlling. And for this object, we will have a mechanical system or a robot, a drone, anything. The decision-making block, which is the controller, gives out an actuation, an action, actuation signal to our object. And we have the sensing, the feedback signal goes back to the controller to be able to calculate our input U. And this sensing could be anything, could be any kind of sensor like camera or encoder or velocity detector, any kind of sensor. Now, what is a control design? Control of tasks and design. The objective of control design is when we have a physical system and we want to construct a feedback control law to make the closed loop system display the desired behavior. So we have a physical system, we want it to display some kind of behavior. Let's say we want H to be stable. We do not want it to be above the level or beneath the level. We have an output flow. So we have to design U so that it keeps H on the level. And control objectives are, for example, we have motion control, which is when we want the hand of the manipulator to follow some kind of trajectory. The force control, when we want to implement some kind of force in the field, using the manipulator or the mechanical system. The hybrid motion force control, when a robot is writing on the wall, on the board, for example, and you have to specify the trajectory, you have to do the path planning and also the force into the board. The impedance control, which is when a robot is used to render a virtual environment. Now, generally, the tasks of control systems can be divided into two categories: stabilization and tracking. For stabilization, a control system is to be designed so that the state of the closed loop will be stabilized around an equilibrium point. For example, we have a walking robot. We want it to be standing in its equilibrium point. We do not want it to be falling. We want it to stay in this equilibrium point. Tracking, the design objective is to construct a controller so that the system output tracks a given time varying trajectory. For example, if we have a drone and we want it to, from T0 to T final, we want it to follow some kind of trajectory in the space. But before we go deeper into this vast field, we need to be able to represent a mechanical system that we want to control. And one of the best ways and powerful approaches is using state space equations, because these equations are can deal with complex and have multiple input and output systems. It might be linear or nonlinear, but for now we will discuss only linear time invariant systems. So state space equations. State of a dynamic system is the smallest set of variables such that the knowledge of these variables at t equals t0 together with the input when t is bigger than t0 completely determines the behavior of our system. So the state is when we want to know the behavior of our system with the input. This state describes the behavior with the input from t equals t0 to t final. The state variables, if we have at least n variables, of course, needed to completely describe the system behavior of our dynamical system. This could be velocities, positions, temperatures, anything. And the state vector is a vector x of state variables, just a vector of these variables, state variables. The state space is a space where its coordinate axis consists of the x1 axis till xn axis. So it's a space with n dimensions that has coordinate axis consist of the axis of the state variables. And here we have the equations x dot equals ax plus bu, y equals cx plus du. A is the state matrix with n by n, b input matrix, n by r, c is the output matrix by m multiplied by n, and d is the direct transmission matrix, m multiplied by r. X is the state vector, u is the input vector, and y is the output vector, as we can see here. And now we're going to the practical part, where we first describe any mechanical system that consists of three main elements, which are the inertia element, which is in our first example here is M, the damper element, the damper here, B, and the spring element, which is K. This mass spring damper system using Newton's second law, of course, everyone remembers it, just to make sure, sigma F equals M multiplied by A. Here we have M, the acceleration equals the sum of forces, minus Kx is the force for the spring, and minus B x dot is the force from the damper. While here we can see that minus Kx is because the force is in the opposite direction of the displacement x. Here also we can notice that that the damper is a function of x dot, not x, the speed of the displacement. And here, to further study our system, we have a new displacement y, and a force is applied u. And using the previous equation, we can write this equation, which describes the dynamical system. It's called the dynamical equation. And we need two state variables to be able to write the state space equations. We choose those as position and velocity, the position y and the velocity y dot. And we have two state variables, x1 and x2. So now we can rewrite the original dynamic equation in terms of x, the space, the state vector, x dot equals x1 dot equals x2 from the definition, and x2 dot is simply this equation. We divide by n and we move these to the other side, and then we have x2 dot, which is y double dot equals minus k over n x1, etc. And this is our final equation of the system. But now we need to represented in vector matrix form. How do we do that? It's very simple. First, we have y equals x1, which is the output equation because we have our output is y. And then we have to write these equations in the matrix form. X1 equals 0 multiplied by x1 and 1 multiplied by x2, which is equal to x2. And x2, of course, we will have this equation plus u over m, which is this one. And y equals x1, as we said before. Now for a little bit more complicated system, the double mass spring system. Here we have two masses that are able to slide on the axis x, and we have displacement x1, displacement x2. Of course, we consider each spring has the same natural length and same spring constant k. Again, using Newton's second law, we can derive for the first mass. We can derive the equation for the first mass and the equation for the second mass. This mass, the first mass, is affected by the first spring and the second spring. And the second one is affected by the second and the third, this one and this one. And here the displacement is the force from the first spring and the force from the second spring. But here we have two displacements. One is x1, x2 is in the direction compared to the spring in the direction of movement x, and x1 in the opposite direction. This is why we have the minus here. And now we can, since we know the dynamic equations for the system, we can now write the state space equations, but we need 4 variables, 2 speeds and 2 positions, 2 displacements. From Z1 to Z4, Z1 equals X1, Z2 equals X1 dot, etc. Z1 dot equals Z2, Z3 dot equals Z4 from the definition. Then we just do the substitution for the Z's into these equations, and we have these following equations. And now we can write the vector matrix form for the state space equations for the double mass spring system. And it goes as follows. Also simple matrix form, Z1 dot equals Z2. Here, by the way, here we have minus 2k over m because we have minus k over m1 multiplied by z. And here we also minus k over m1 multiplied by z1. And of course, this z3 here is multiplied by k over 1 plus, and the others are zeros. So now, since we have written these equations, we still need to make sure that these equations are correct. So what do? We just simply multiply these matrices, and we should have the same equations for the system that we have written, the equations of motion. Here we can have multiple inputs or just one u, either for m1 or for m2. Now, if you can try to write the state space equations for the car suspension system, as you can see here in this figure, and you can also write it in vector matrix form, as we showed. How many state variables do you think we will need? Next lab, we can solve it together, but here's a little hint. The dynamic system, the dynamic equations of the system. And to wrap up, we have learned in this lab about robot control, the tasks of control system, and objectives, the state space equations, and we provided an example. I would be happy if you can provide an example for a for a system that we need to write state space equations for that we didn't mention here. If you have any questions, don't hesitate. Thank you very much. Here are the references. Thank you for your time, and thank you for your attention. Goodbye.